Started, so first seminar of the spring semester, and we have Bob Penna visiting from MIT, and he will tell us about membrane paradigm and black hole astrophysics.
Thanks a lot. Thanks a lot, and for the invitation and spending a couple of days here. It's been really nice. So thanks everyone. Membrane paradigm and black hole astrophysics. So the membrane paradigm is an alternate or dual way of talking about black holes, where you throw away the usual black hole interior, and instead you put a fluid viscous membrane on the event horizon, and then all of your black hole physics becomes the physics of interactions with this membrane. And I'll explain more about that in a second. But I like the membrane paradigm for two reasons. One reason I really like it is because it just turns out to be useful for understanding practical problems in astrophysics and doing calculations in astrophysics. And then the second reason I like the membrane paradigm is because it looks to be related to deep things in fundamental physics. So it has a lot in common with things like the holographic principle. And so the hope is that the membrane paradigm can be a link between those two subjects, between astrophysics and fundamental physics. It can lead to interactions between the two. And I'll try to give some examples in the talk of those interactions in attempts to sort of make those connections. Okay, so the outline of the talk is I'll start by reviewing what the black hole membrane paradigm is. And then I'll talk about some applications. I'll talk about astrophysics of jets from spinning black holes, and then jets from boosted black holes, where the black hole is moving along and you're extracting the energy in its motion. And then I'll talk about something more theoretical at the end, some recent stuff about this so-called BMS Group of symmetries, which governs gravitational scattering, and how you can understand that using the membrane paradigm. Okay, so let me start by reviewing the membrane paradigm. So why would you arrive at such a thing if you were discovering it on your own? Okay, so here's the idea. This picture on the left is supposed to represent the Penrose diagram of a black hole. And the way we arrive at the membrane paradigm is we're just going to think about observers who spend their whole lives in the black hole exterior. So they never jump inside the black hole. So here's the exterior, here's the black hole interior. This diagonal line represents the event horizon. This is maybe a collapsing star that formed the black hole. And here's an example of an observer who spends their whole life in the black hole exterior. So we just want to think about those guys. And an example of such an observer is an astrophysicist, because astrophysicists spend their whole lives studying black holes, but they never go inside them. Okay. And then the next thought is that, a principle of physics is try not to discuss things that can't be measured, even in principle. Okay? And for this family of observers, they can never measure anything about the black hole interior, even in principle. And so what we're going to try to do is formulate all of their calculations in a way that never references the black hole interior. It seems like it must be possible. After all, by definition, signals from the interior can't infect anything in the exterior. Okay, so the first thing you could try to do is just throw away the black hole interior. And I'm just going to do all my black hole astrophysics on this space-time that just ends at the horizon. I should be able to. These signals can't get out anyways. So that's the first thing you might try. But you'll find, and I'll show you an example in the next slide, you'll find that you run into some problems where things aren't consistent when you do that. And so to fix up those problems, you have to introduce a membrane on this new boundary of space-time that you've created. And you define this membrane to have properties just right to reproduce physics in the exterior correctly. So let me give you an example of why you'd be led to add this extra membrane when you're working on this space-time that ends at the event horizon. You're not talking about the interior. So here's a problem that comes up in astrophysics, and it'll come up a little later when I talk about jets. Here I'm thinking about a black hole immersed in a magnetic field. And so I've drawn like this toroidal magnetic field. And in the usual thinking, there's nothing special at the event horizon. And so the magnetic field just continues smoothly into the black hole interior. Okay. But now I want to try to do things in this membrane way where I don't talk about the black hole interior. So I switch to this picture on the right where the magnetic fields just abruptly end at the event horizon. Okay, but that's created a problem because I've broken Ampere's law. So Ampere's law tells you you're not allowed to just truncate a magnetic field. Only currents can do that. And so to restore consistency with Ampere's law, you have to endow the horizon, this membrane, with a current. And you define the current to be just the thing that it needs to be to make Ampere's law happy. And so in this configuration, you arrive at this current. It turns out the current has to flow along theta. That has to be the magnitude. And then now Ampere's law is satisfied in this description. So it's through a series of thought experiments like this that you can work out all the properties that this membrane must have. And through a similar series of thought experiments, you find all these amazing properties. And so this was worked out in a series of thought experiments in the 1980s. In addition to carrying this current to satisfy Ampere's law, you find that the membrane is a fluid and it obeys precisely the Navier-Stokes equations. It has to have a resistivity and a viscosity, and you can compute them. It has a stress-energy tensor, and the energy and angular momentum of the black hole are smeared out and stored in that stress-energy tensor on the horizon. And so on and so on. You could add all sorts of properties it has.
So are these things self-consistent? When you presumably you check
so
some of these properties that
so then
are actually...
Yeah, you might worry that, you derive two properties it has to have that conflict with each other, and then the whole thing falls apart. And I think that's a reason a lot of people weren't very quick to adapt this way of thinking, because they worried somewhere there would be, two properties that conflict. So this way of getting it by a series of thought experiments is sort of the 1980s way, but there's a much better way to get it to derive this now. Well, there's actually several. And they're more mathematically rigorous, and it's just clear from the mathematics that every step is justified and that it's all self-consistent. And so the really nice way to get it, in 1998, Parikh and Frank Wilczek, they have a paper on the membrane paradigm. This is what I'd recommend as a starting point if you want to learn how to do it in a modern way. They derive all the properties of the membrane from a nice action principle formulation. And it's just very transparent and clear that everything's mathematically rigorous and that there's no inconsistencies. And then there's other perspectives as well. It's interesting, you can derive it a few different ways. So there's this interesting paper by Balachandran in 1994 where he derives it, and the whole story is about gauge invariance. And it's all about the fact that having a hard horizon boundary breaks gauge invariance, and to restore it, you need to put some edge states on the horizon, and the membrane paradigm is those edge states. And it's related to something actually that Gia talked about in a paper very recently, with breaking gauge invariance and needing extra edge states connected. And then Hong Liu, who spoke here on Wednesday, has also written about the membrane paradigm. And in his language, it's derived as an IR limit of a renormalization group flow in a holographic setup. So there's all different ways of thinking about it. But that's a good paper to start with if you want to actually learn it well. Okay, so one contribution I made to thinking about this membrane paradigm is for some of the black hole jet problems that I'm going to talk about in a second, it turns out to be really useful if you have a version of the membrane paradigm at infinity. Also for applications to the fundamental physics questions, it's nice to have a version at infinity. So it turns out that, so in asymptotically flat spacetimes, if you go out to infinity, infinity is a null surface, and it turns out that null surface also behaves like a fluid, and it has a membrane paradigm description. So you can pick your favorite derivation on the previous slide, and you can go through all the same steps at infinity. And then you find that future null infinity behaves like a fluid, it has a viscosity, it has a resistivity. So in this paper, I did that exercise, and I worked out all the properties of membrane paradigm at infinity. And the useful thing for this talk, for the next section, is that it turns out both membranes have the same surface resistivity. They both have a surface resistivity of this magic value 377 ohms. Yep. And the fact that there is a membrane paradigm at infinity isn't too surprising if you stare at the Penrose diagram long enough, because it has sort of the same causal structure as the horizon. And ultimately, all these magic properties have to do with the causal properties of null surfaces.
So just to understand, so this is for the space in which there is one black hole, you're looking at future infinity and deriving that, or
This thing at infinity would work for any asymptotically flat space-time. Yeah.
empty space time as well?
Yeah, even just Minkowski space,
But
future
why
null
would
infinity.
you have membrane at infinity for empty space time?
Yeah, so I guess all the charges in the stress energy tensor would be really boring and trivial. So, But in that limit, I mean, yeah, everything would just be kind of trivial in that limit.
Okay,
But
so that's an for your charges.
but if you have this Minkowski space and you're thinking about some gravitational wave scattering problem on top of it, you could think about it in terms of, and that's actually what I'll get to at the end of the talk with BMS stuff. Yeah, with BMS Group.
That's what my question for. What geometries do you have that non-trivial that you fit in?
Yeah, any asymptotically flat geometry has all the structure at infinity of a membrane and a fluid dynamics, and so gravitational scattering problems can be interpreted as gravitational waves hit the membrane, hit null infinity, and excite this degrees of freedom in the membrane, which in Andy Strominger's language, he would say gravitational waves hit this null boundary and excite soft gravitons in null infinity, and that's just like ordinary particle physics way of describing scattering in just like boring Minkowski space. You can rephrase that in a membrane way where these soft gravitons on the boundary become the membrane stress energy tensor. So even in that case, there's some interesting things to talk about. Yeah. Yeah. These boundary degrees of freedom have this membrane interpretation. Yeah. That's kind of the last part of the talk. But
and this resistivity doesn't depend on spin.
no.
Charge if it's a charge black hole. It just depends on having a null horizon.
Yeah, so the resistivity has like a really easy two-line derivation. So one line is that, as I showed in one of the very first slides, you need to endow these null surfaces with currents in order to terminate the magnetic field and agree with Ampere's law. There's plus or minus signs depending whether you're at the horizon or at infinity. And then the second thing is that at these null surfaces, because they're null, you can have electromagnetic waves going in one direction, like ingoing but not outgoing, or in this case outgoing, but you can't have waves coming in. And as a result, you get a constraint that the electric and magnetic fields have to look perpendicular to each other. It turns out, and then when you combine those two facts alone, you get so this is this. You just get Ohm's law, and when you put units back in, you find a resistivity of 1 over speed of light times vacuum permittivity, and that thing, if you ever compute it, is 377 ohms. So it's almost trivial. It's really just these two facts. Yeah.
Say all the same words about any null surface. So is it that
Yeah, according to some observer, so some observer, you'll get, yeah. This will be true at any null surface. These null surfaces are special because of this property, and that they're boundaries for this guy's causal diamond. But you could also consider, you could also think about observers who jump in the black hole and hit the singularity. They have some causal diamond, and on the boundaries of their causal diamond, you can set up the exact same membrane paradigm stuff, and you'll find this 377 ohms. And this is very much related to, there's this famous thing in holography about this universal viscosity to entropy ratio of 1 over 4 pi that a lot of theories saturate. And this is like the resistivity version of that, like universal thing. Yeah.
But this goes back to the 70s, right?
Yeah. And that viscosity to entropy ratio that's become so famous recently also goes back to the 70s in the context of horizons. But now people are realizing how general these things are, and they're important in limits of all kinds of things. Yeah. Yeah. Okay, so now turning to applications of this. So the first application is about black hole jets. So here's a picture of a jet from Centaurus A, and you're seeing a galaxy edge on, and there's these powerful outflows. And the interpretation is that these outflows are drawing their energy from the spin of a black hole. And there's a standard model for black hole jets. And the standard model of black hole jets is the Blandford-Zanaik model from 1977. And it almost gives you the jet power from first principles. There's one free parameter in the model that you have to just put in by hand. And that free parameter is, people call it omega f. It's the field line velocity. It tells you how fast the magnetic fields are going around, the angular velocity of the magnetic field lines. And it's a free parameter of the model. You have to just measure it somehow and then put it in by hand. Once you do that, you're off and running and good to go, and you can calculate jet power and everything you want to know about jets. And so the way people determine what this number is, or this function worth of numbers is, and in order to complete the model, Well, the way they do it nowadays is they run simulations. So that's one of the things I've done. I've run general relativistic magnetohydrodynamic simulations. And so what you do is, in these simulations, is you have an accretion disk accreting onto a black hole, and it's bringing on magnetic fields, and the black hole is becoming magnetized, and you just sit back and let the whole system relax. It forms jets spontaneously, these Blanford-Zanayak-like jets. And then when the simulation has reached its equilibrium, you just go in and look at the data, and you can just measure what omega f is. And you can repeat this over and over for different initial conditions, for different black hole spins, etc. And so I've done a series of these experiments, and other people have looked at it in similar ways. And what I find, what everyone finds, is that there's this incredible universality, which is that this free parameter, or it really could have been a function's worth of free parameters, has this universal value of that omega f is always sitting right about at a half omega h, where omega h is the angular velocity of the horizon. So if you have a spinning black hole and you take some magnetic fields and just throw them on the spinning black hole and you wait long enough and come back, you'll generically find the field line spinning around at half the angular velocity of the horizon. Okay, and knowing that is enough to go plug it into the Blanford-Zanayak model and start computing jet powers. But I spent some time trying to understand why it always came out to be this universal half. Why not something else, or something that depends on parameters? And the only and the way I was able to find a nice explanation was by recasting the problem in this membrane paradigm language. And it turns out when you look at it in that language, there's a really nice explanation of what's going on. Okay, so in this part of the talk, I want to explain that explanation for why this always came out to be a half. Okay, so here's my problem. I have a black hole and it's embedded in some magnetic field, so I've drawn the poloidal magnetic field that it's sitting in. I've drawn a very simple thing with just radial magnetic field lines, but that's not essential. These field lines could have any shape that you want, essentially. And then because I'm going to do this in this membrane paradigm setup, I've drawn my a heavy blue membrane at the horizon, and then I'm also going to use this new ingredient that I introduced and talked about, this membrane at infinity. Okay? Okay, so there's the magnetic field. Black hole magnetospheres also have electric fields. To a high approximation, they satisfy something called the force-free condition, which forces the electric field to be perpendicular to the magnetic field. So in this setup, the electric field lines would be doing this thing. So that's what the electric field would look like in the magnetosphere. In addition, these magnetospheres have currents flowing around. And the same force-free condition also forces currents to flow along magnetic field lines. So currents would be flowing along magnetic field lines. So this is what the currents would look like. And now if we weren't doing black hole membrane paradigm, we would stop, and this would be the problem we'd think about. But one of the first things I told you is that in the membrane paradigm, to get everything self-consistent, you also have to include membrane currents that flow along the membrane, that guy I talked about in the beginning. And so if I add those to the picture, this is what the picture becomes. You get a current flowing along the horizon, and you get another current flowing along infinity. And you can check, you can go through and check carefully that the total currents form closed circuits, and that charge is conserved around these circuits. And so the really interesting, nice thing is that the jet problem becomes reformulated as a set of circuit equations.
Could you explain, so what's the physical origin of this force-free condition? So where it's coming from?
The origin of the force-free, so the force-free condition is valid whenever the electromagnetic energy vastly exceeds the inertial forces in the particles, and these jets are very highly magnetized, so that's a really good approximation. And in that approximation, you can assume the Lorentz force vanishes, because if it didn't, then you would have, if Lorentz force, particles would move around to try to cancel it out. And so if you set Lorentz force equals to ma, and the particles have negligible inertia, you're in a limit where the particles can short out any Lorentz force that appears. So you're in a limit where the Lorentz force is 0. And then by writing out the Lorentz force and taking dot products with J and B, you can derive those properties I just mentioned. Yeah. And in all astrophysical jets, this is a good approximation, because these jets, and I can talk about simulation data showing this and there's observational data, are super highly magnetized. So the particle inertia is really negligible, so you can make these approximations.
At the infinity?
Yeah. Okay, good point. So, so for sure, no real astrophysical jet goes to infinity. So this is an idealization. And I wasn't going to go into it in the talk too much, or at all. But yeah, certainly any real jet has some finite extent, and then it starts interacting with, intergalactic medium or interstellar medium or other messy astrophysics things. And so it doesn't actually get all the way to null infinity. The point is, the point is as long as you're well outside the sonic points of the jet, you can treat the outer parts of the jet as effectively at null infinity, and the same thing works. Yeah. As long as you're well outside the sonic points of the jet, you can imagine you're at null infinity and set up the same thing. Yeah. Okay. All right. So.
This approximation is basically that all charges move at the speed of light along magnetic field lines. Is that correct? Is that why you keep talking about null infinity?
Yeah. So there are the two conditions I wrote. The first one, that you need a current to cut off the problem. You can put that on any surface. You can put that on a time-like surface. You can always terminate a magnetic field by putting some current that just ends it. And then that second condition was that all your waves are outgoing. All your electromagnetic waves are outgoing. There's no waves coming back in. Yeah, as long as you're beyond the sonic points, that's a good approximation. Because beyond the sonic point, things can't come back upstream. Everything's going out, and it's going out at the speed of light. It's going out at the speed of light. Yeah. So it's not. I agree exactly with what you said. I just had to think through it a second. But yeah. I just in my own. Yep. Okay. So the jet. You set things up this way, and the jet becomes a circuit problem. It's a 3-element circuit. So the black hole acts as a voltage source. It also has an internal resistance, that 377 ohms. And then there's also a resistor at infinity, another 377 ohms. So you solve the equations become solving these circuit equations. And the astrophysical observable that an observer would measure is power dissipated in the resistor at infinity. That's the Blandford-Zerniak jet power. It's the power dissipated in the resistor at infinity. And the mystery parameter that we all want to know why it's always comes out to be a half, when you reformulate it in this language, it's exactly the thing a circuit textbook would call the circuit efficiency. So the fact that this kept coming out to be a half was telling us that circuit on the previous slide tends to have an efficiency of 50%. Okay, why does this circuit efficiency tend to be 50%? So the circuit efficiency, it's precisely given by this formula. And it has to do with the ratio of the resistive change at the load at infinity and at the horizon. And just as for ordinary circuits, you get maximum power at the load when you have perfect impedance matching. So that's a general property of this equation in just ordinary circuits. 50% efficiency, this thing being a half, gives you the most powerful jets. It gives you the most dissipation at the load. And it corresponds to perfect impedance matching between horizon and load. So the problem of why is this always a half becomes why is there always basically near perfect impedance matching between horizon and load. But that's just because they both have the same resistance of 377 ohms. If that was the whole story, then this thing would always be exactly a half. It can differ from a half by a little bit. And the reason it can differ by a little bit is because these delta r's in that formula, I can show you the formula on the next slide, but delta R is 377 ohms times some geometrical factor. So 377 ohms is the surface resistivity of these membranes. But the current experiences a larger resistive drop or a larger voltage drop the longer it spends sitting on the membrane. And so the real formula is 377 times some angular factor. And so to really have perfect impedance matching, you also have to have the same angular factors on both membranes. And so totally radial fields are the ones that have the same, delta thetas here and here. and so the same resistive changes, because they sit there and soak up the same amount of resistivity. And so these guys have perfect impedance matching, efficiency of a half, the most powerful jets. If you collimate your magnetic field, then delta theta up here is smaller than delta theta down here. So these guys are underloaded. These field lines will have a omega f less than a half and slightly less powerful jets. And you can also have field geometries where the magnetic fields open up. Those will be overloaded. Omega f will be a bit greater than a half, but also less powerful jets. The most powerful jets is this case. But the dependence on the field geometry, it's given by this formula. It's a pretty weak dependence. So as long as you don't do anything too absurd with your field lines, omega f over omega h always lands around a half. Yeah, so that's the explanation of why it always lands around a half. And the point is that I don't know another way to see this so clearly, except reformulating it in this membrane paradigm, vaguely holographic way of looking at the problem. And then you can test that this is what's really happening with the simulations. So here's the simulations I mentioned. This is one of my general relativistic magnetohydrodynamic simulations of a black hole jet. The black hole is in this centermost pixel. It's being fed by an accretion disk, which doesn't show up in the plot, but there's an accretion disk bringing fields onto it. And then it spontaneously develops a jet. So what I'm plotting is the Lorentz factor of the jet. It's hitting Lorentz factors of 4. So this is the simulation data. The simulation doesn't use the membrane paradigm in any way. It just does its thing in ordinary black hole problem setup. But after I run the simulation, I find it really useful to take the simulation data and translate it into the membrane paradigm story. And so if I zoom in on my simulation data here, I can take the simulation data and I can use those formulas I wrote down, and I can compute the membrane current that I mentioned, J, that lives on the horizon. And this is the actual simulation data of what it looks like. This is the membrane J flowing along the horizon. Yeah, and actually the arrows are converging. They flow back out in the disk. They return through the corona. You get these closed circuits. And so the nice thing is you can go through the simulation data. You can compute each term in the model. So here's the actual GRMHD simulation data. This is a black hole described by the Kerr metric with a spin parameter of 0.9, so it's spinning near the speed of light. I've taken the simulation data, translated it, and here's the power generated by the voltage source on this membrane at the horizon. Not all of that power ends up in the jet because some of it is dissipated by the surface resistivity of the horizon, and so here's the simulation data shows for that. And then the result is the actual power dissipated in the load, which is the actual jet power that you'd actually compare with observations. And you can just check that each of these terms is doing exactly what you expected based on the model. So this gives a really concrete demonstration that we really understand how these black hole jets work in the simulation, and that the explanation I gave with cartoons earlier is really on the right track.
Just technical question. So you just input the Kerr summation in it with smoothing some singularity somehow, and then put the hydrodynamics in that background and run.
Exactly. Yeah. We throw away the numerical grid stops inside the horizon, but before the singularity, any gas that hits the inside of the grid just flows out into, just disappears. It just flows out. So yeah, so it's just but a fixed Kerr metric, and then the fluid and the magnetic fields, and that's all just like a test field on top of it, on top of the Kerr metric. Yeah. And
if I remember correctly from a discussion earlier this morning, it seems like you only see this for disks, not for all kinds of setups, for all initial conditions, but specifically for disks that are thick, relatively thick.
Yeah.
So what in this membrane kind of setup, what would be there the kind of physical reason why it all have impedance matching and all these fun things? Why it happens only for the accretion disk setup that is actually very astrophysical? Yeah, so that's an interesting astrophysics question. It doesn't. So what Miriam's referring to is the fact that so I've picked a simulation that has black hole jets. I've done many of these simulations with different parameters to explore different astrophysics questions that I don't have time to get to in the talk. But one of the things you can do is you can look at accretion disks with different thicknesses. And so it turns out that to see jets in the simulation, to see these jets form, you have to use a really thick accretion disk. And that's because really thick accretion disks are really good at dragging magnetic fields onto the black hole. They have large radial velocities,
and they're not very turbulent, so the field has trouble diffusing back outwards, so they drag a lot of field onto the hole and make powerful jets. You can do another case where you have these thin accretion disks. You just tune down the thickness of the accretion disk, effectively by making it more changing how it radiates. And if you make the disk very thin, then it has trouble building up a strong magnetic field on the black hole, and a jet never forms. So it's a really interesting problem. But because that's all happening in the black hole exterior, and it doesn't really involve physics at the horizon. It involves physics of the disk. It's not something you'd think about using the membrane paradigm, but it's still something fun to think about. But it has to do with the physics of diffusion and advection in the disk and how they balance each other as a function of disk thickness. Yes, but so yeah, membrane paradigm can't be applied to every problem, but anything that involves an interaction with the horizon. Yeah.
Is there any similar thing that, like, if you have a pulsar, you have this similar physical setup, except the bottom surface is like the surface of a neutron star?
So you can set up the same circuits with a pulsar, and the fun thing is that, so this formula, you can set up the same circuit with a pulsar. The difference between a pulsar and a black hole is that a pulsar, unlike a black hole, a pulsar is a perfect conductor. So to take the pulsar limit of all of this delta RH becomes 0 because the pulsar is a perfect conductor. So in that limit, this ratio just becomes 1 because this is blowing up because delta RH is now 0 because it's a pulsar. So this just becomes 1, which is telling you that field lines rotate at the same speed as the pulsar, which is correct. That's what pulsar field lines do. They're frozen into the star and they rotate with the speed of the star. Yeah.
The project to the 6G simulation.
Yeah.
So over there, obviously you have some grid which kind of cuts horizon as well, in addition to cutting the singularity, I suppose.
It's inside the grid ends inside the horizon.
But you don't have resolution. You don't have infinite resolution, right? I'm talking.
That's correct. Yeah. There's absolutely.
Yeah. At the horizon. So those sorts of effects are somehow smoothed out for you. So even in that sense, you are using some sort of brick wall model for a black hole. What is it?
The simulation's not doing anything like so. So the simulation has some black hole event horizon.
Except that that line is smooth now, right?
Yeah, and then when we resolve it, so here's our grid cells. And so the horizon's getting blurred out, into a grid cell. Gas is falling through in the horizon. Gas falls through the horizon. So there's some surface here that's behaving like a horizon, but everything's blurred out by the grid cell size.
But you don't need to impose any boundary conditions at that point.
No, because the inner boundary of the grid is far enough away from here. The only place you have to put a boundary condition. So here the only place you have to put a boundary condition is inside the black hole. So if, these are your grid cells.
Okay, yeah, you're right.
You just have to put boundary condition here, and then we're working in Kerr-Schild coordinates, or maybe I should call them Eddington-Finkelstein, because Finkelstein just passed away. But working in basically Eddington-Finkelstein coordinates.
Oh.
So the simulation is thinking like an infalling observer and computing everything, and then I translate everything into this frame.
Oh, that's the answer.
Yeah.
Because you don't have that surface at all.
Yeah. Okay. Okay, now I'm going to talk about another application. So that was jets from spinning black holes. Now let's think about a problem that's only attracted interest more recently. So this is a cartoon that's supposed to be a black hole neutron star binary. And this is becoming interesting as LIGO starts to come online. And because in the final stages of its inspiral, this thing can be a strong LIGO source of gravitational waves. We'd like to find electromagnetic counterparts to these events. You get an interesting kind of jet in this case, we think. So now the black hole will be moving around through the strong magnetic field of the neutron star. So there's a new energy source. So before, the jets were being powered by the energy stored in the spin of the spinning black hole. Now the jets can be powered. They can extract their energy from the orbital motion of the black hole. So there's orbital energy available to be tapped by the jet. And This problem, surprising, like the Blandfords and Ike jets, which have been thought about for a really long time, there's almost very, very little has been written on this, and only in very recent years. And so even there aren't even simple analytical models for what to expect. There's just almost nothing. Just a couple simulations recently. There's very little work on this, and it raises some basic physical questions, which are fun to think about. There was one of the earliest people to point out that this was possible was Sean McWilliams and Jan Levin 4 years ago. Drew this cartoon of what I just described and said maybe, and then they did some back of the envelope estimates of what the luminosity could be for this process. So the full problem is very difficult. The metric of a binary black hole is a mess. But there's a simpler problem that can give a lot of insight, which also hasn't been explored very much, which is just to consider a single black hole. It can even just be a Schwarzschild black hole moving through a uniform magnetic field. And the idea is that interactions of the black hole with the magnetic field will exert a drag on the black hole, and some of the energy in the black hole's motion will go out in the magnetic field. And you can think about this like we've taken that binary problem, we've just really zoomed in on the black hole so that its orbital motion just looks like, so this velocity is like a stand-in for the orbital velocity. But this is a simpler problem that you could hope to tackle analytically before moving to simulations, and it hasn't been tackled analytically, so I spent time thinking about that over the past couple of years, and I'll tell you just some basic results. There was a group, Nielsen et al., Luis Lehner's group, who put this problem on a computer, and then they let it run, and they looked, and lo and behold, they saw energy outflows. So that's some experimental data that there's some energy outflows. But yeah, it's puzzling to understand it analytically what's going on in those simulations. But that was the motivation.
Is this actually the same, or is this actually similar to the orbital case? Because maybe I'm not thinking about this enough, but in the orbital case, I imagine you go to a co-rotating frame where it's not actually moving with respect to the magnetic field.
Oh, so yeah, I don't think that's quite right. So in the orbiting case, well, the picture we're going to have in mind is a black hole going, the neutron star is a really strong magnetic field anchored in the neutron star. The black hole can be orbiting relative to that field.
Oh, I see.
They're not locked. Yeah.
Okay.
Yeah.
Also, you could imagine a parameter of the problem being the angle between the velocity vector of the black hole and the background magnetic field.
Yep. And the spin of the black hole gives you another angle to play with. So there's all sorts of interesting, things to look for. Okay.
So if you did that with a conductive ball, there'd be eddy currents.
Yeah.
That far out of the ball.
Yeah, you're jumping ahead actually. Okay, so that's the membrane paradigm analogy type thinking, but I'll mention that in the end. Okay, so this problem is nice because you can tackle it analytically. So the simplest thing you can do is you can just start with a Schwarzschild black hole. And and if you write the Schwarzschild metric in these funny Kerr-Schild coordinates, then it's really easy to obtain the metric for a Schwarzschild black hole moving with constant velocity. You write the metric in these funny coordinates, t, x, y, z, and then you essentially just apply a Lorentz boost to those coordinates. It just looks like an ordinary Lorentz boost, but it turns out that's the right thing to do. And you arrive at some new prime frame. And observers in the prime frame see the Schwarzschild black hole moving along with a constant velocity. So you've added this parameter v, which is related to the velocity of the black hole, and a parameter gamma, which is like a Lorentz factor. And it looks like a black hole moving along in the plus z direction. This is for Schwarzschild. It's really easy to do this for Kerr as well. Kerr, you can write down in Kerr-Schild, and then there's a simple coordinate transformation that gives you a moving spinning Kerr black hole. But let's just stick to this case for now. Some properties of this metric describing the moving black hole is that it's a vacuum solution of Einstein equations, as it has to be, because it's just related to ordinary Schwarzschild by a coordinate transformation. Event horizons at r equals 2m. When you boost it, the total area of the horizon stays constant, but to the observer who it looks moving, the horizon appears to be squashed and sort of pancake-like, so the geometry changes. And now the first thing I'd like to talk about is just to even understand conceptually what's happening here is confusing, and it took some sorting out. Just to understand what it means to take energy away from a Schwarzschild black hole, that seems kind of strange. Schwarzschild black holes are supposed to be ground states, and you're not supposed to be able to get energy out. the reason you're able to do it has to do with the fact that energy is really subtle in general relativity, and so there's actually there's many definitions of it. So I want to talk about 3 different notions of energy of this black hole, and I think that'll clarify what's happening in this process. So quickly, the first thing is, to any black hole you can compute something called its ADM form momentum. Suffice to say, it's some integral that you compute over some combinations of curvature at infinity, and you do this integral and it spits out a 4 vector. And that 4 vector has an interpretation as the form momentum of this entire black hole spacetime. And if you do that for the Schwarzschild black hole sitting at rest, that's the 4 vector that gets spit out. Schwarzschild black hole at rest has energy m and it has no 3 momentum. If you do this, if you compute this ADM form momentum for the moving Schwarzschild black hole, it spits out this form momentum, which is what you'd expect from particle mechanics. It looks like a particle with energy that's been boosted to gamma m, and it looks like it has 3 momentum gamma mv. In addition, black holes have another kind of mass, so a third notion of mass and energy for a black hole called their irreducible mass, which is related to, you compute it by taking the area of the event horizon and some square roots. And the interesting thing is that both black holes, moving and sitting still, have the same irreducible mass, related to the fact I mentioned earlier about the area of the horizon being the same in both frames. And one thing we've learned from thinking about spinning black holes is that if you have any energy in excess of the irreducible mass, that energy is available in principle to be extracted. And so the guy sitting at rest doesn't, but the guy who's moving along has energy gamma m, which exceeds m, and so there's this difference, gamma minus 1 times m, which is available in principle to be extracted. But a weird thing about it is that this is an observer-dependent notion of energy. It's the time component of this form momentum. So as the black hole goes through the magnetic field, and I say, oh, the magnetic field is extracting energy from it, another observer in a different frame will have a very different interpretation. It'll look like the field is moving and giving energy to the black hole. So whether or not energy is coming out depends on the observer, but that's the same in when you're scattering billiard balls. If you define energy as a time component of momentum, it's a frame-dependent thing. So which billiard ball gives energy to the other billiard ball depends on which observer you ask, which is different from spinning black holes, because there's another notion of energy. You can take the norm of that ADM form momentum, call the black hole rest mass. Spinning black holes, when they lose energy to Blanford-Zernike jets, their rest mass, this notion of mass, actually goes down. The process we're talking about now, where a black hole moves through a magnetic field, this always goes up. So when you talk about extracting energy from a spinning black hole, it's an observer-independent process. Everyone agrees that this mass is going down, and we all agree. This notion of extracting energy, a black hole going through a magnetic field and getting its energy out, is observer-dependent. So we're talking about this notion of energy, and only some observers see it that way. But there are astrophysical problems where it's useful to think of in these terms. I spent a lot of time talking about all of that, but I think it's useful. Otherwise, it's conceptually confusing what it means to take away energy from these moving black holes.
Could you please repeat in terms of the invariant mass of the next slide?
Yeah, what happens?
Yes,
In the spinning case, Blanford-Zernike jets from spinning, it goes, yep. In this case, this always goes up. In these processes, that always goes up. Yeah.
How long does it take for the black hole to come to rest?
Yeah, good question. I guess it depends how strong the magnetic fields are and how fast it was initially moving. We have solutions for the jet power, so you could integrate those solutions and answer. But I don't know off the top of my head. It's long. I mean, it'll be comparable to the amount of time it takes a spinning black hole to come to zero spin, probably, is my first guess. So a long time, but I'm not exactly sure. I'd have to think more. Yeah. I mean, the problem we have in mind is the late stages of a LIGO merger, and okay, it only has a few orbits before it's just going to merge, and so there doesn't have time to come to rest. But anyways, yeah, it's an interesting question. It doesn't even take enough energy away to really influence the orbits too much. You can still the gravitational wave information will always be dominant. But anyways, good question. Good question.
Is that true, that last statement you made? Is that true throughout the entire in-spiral, starting from far out?
I think so, because I think when it's small radii, at large radii, the gravitational wave emission isn't so powerful, but this isn't so powerful either because your orbital velocities are small, and we're going to see in the end that there's a factor of v over c squared in the power. So it may technically win at large radii, but then be so negligible that it's just not interesting anyways.
If it wins, then it drives the end spiral instead of gravitational waves.
Yeah, but it might be just so, you might have to go out to such a radius where it's so negligible. I don't know. Maybe it never wins. I don't know, actually. I haven't thought about it. Yeah. There'll be these competing effects, though. Okay, so that was Gregory's question. Yeah, yep. Okay, talked about that enough. All right, so now we're building up to the problem of understanding jets. The next thing you'd like to understand is for spinning black holes, one of the things that really helps to think about is the fact that a spinning black hole has this region called the ergosphere, where you can have negative energy. And no one had really thought about the ergosphere of a moving Schwarzschild black hole. But it turns out it's something you can think about. So in these coordinates, where the black hole is moving along, just like in the Kerr case, in both cases, there's a region where, with respect to those coordinates, observers cannot remain at rest. And that region is called the ergosphere, and inside that region you can have negative energy. And if you look at that region in our problem, here's my black hole moving along with velocity v. And I've computed the position of the ergosphere as a function of black hole velocity. There's a simple formula for the shape of these curves, a really simple formula for the outermost point. Interesting things about it. First of all, for a Kerr black hole, spinning black hole, the ergosphere is always centered on the black hole event horizon. For these guys, the ergosphere lags behind the black hole in a funny way. Another interesting thing is for a spinning Kerr black hole, the ergosphere has some finite extent. So no matter how fast you spin the black hole, it can never expand beyond this limit of 2 gm over c squared. But for these black holes, actually the faster you go, you can make this ergosphere arbitrarily large, which is kind of weird.
It should become a shock wave.
Actually, it just gets bigger and bigger, and then the limit, it would fill up all space in a weird way.
I thought the limit of infinite boost of this thing was an Eichelberg-Sexel shock wave, which has the property that if you're sitting there and it passes you, it changes your velocity suddenly.
Yeah, that's a weird limit where the black hole itself becomes null.
Right.
Something funny must happen in that limit. I'm not sure, actually, how to think about this would be Eichelberg-Sexel shock wave. Yeah, that's a weird limit because the black hole is becoming null. It's becoming, and that's also a weird limit because in that limit, yeah, that's the limit where you take c to 1, but to keep gamma m finite, when you take that Eichelberg-Sexel metric, you also have to send m to 0, so the black hole is becoming a point, so it's a weird limit, but it's a fun limit to think about. Okay. All right, so I'm trying to build up step by step to thinking about this process. So the next thing is, once you have an ergosphere, you can do what Roger Penrose did for Kerr black holes, and you can think about the Penrose process. It's a nice simple warm-up to thinking about the full black hole jet problem. So the Penrose process is, if you haven't heard about it, what you're doing is you're sending in particles with positive energy into the ergosphere. You're letting them decay. And then one of the daughter products falls into the black hole with negative energy, and the other one comes out with more energy than the one you threw in. And so it's a nice proof of principle that you can extract energy from spinning black holes. And you can do the same thing in this case to convince yourself that in principle it's possible to get energy out. And so one of the things I did is find, so these aren't cartoons, these are actual trajectories where particle A comes in, this thing is moving near the speed of light, so it has a huge ergosphere. It splits, and you find some negative energy trajectory that falls into the black hole, and B comes out with more energy than A. So it's like a proof of principle. You convince yourself this is really possible to get energy out. Maybe it could be interesting astrophysically. It might be fun to think about. I haven't thought about, but you could imagine A is like some star that gets disrupted into two streams or two pieces, and one falls in and one comes out with more energy. I don't know.
Sorry about that.
Yeah.
So you're saying if I start to accelerate it, the ergosphere becomes bigger and bigger.
Yep.
And total negative energy then would be bigger and bigger, I suppose. If I integrate that,
you have a large, yeah.
volume,
Okay.
so
This huge region where you can have negative energy, measured by these observers who see the guy moving.
But in terms of that negative energy being used to accelerate the hole itself, I mean, you are using now that energy in the Penrose process to convert into particles.
Yeah. So this process is going to slow down the black hole a little.
Sure, but
Yeah.
how about that energy being used to hole itself in that process is that, because naively it would look like I can do that, but there must be something wrong with the logic that I'm just presenting. So in that case, the hole would actually by itself.
I'm not sure it's possible. I'm not sure.
It shouldn't be possible.
It shouldn't be possible.
Yeah.
I think what you might be thinking about is a comment I was going to make just like at the very end and future directions, but there's a very similar process, which I wasn't going to mention at this point in the talk, super radiant scattering. And once you have an ergosphere, there's ways to exchange energy with black holes by scattering waves super radiantly. And anyways, it looks like that isn't what you're thinking about. But anyways, there's some paradoxes that haven't been fully understood about what you can do in this case that I was going to mention in the end. I'll comment on the end about problems with, like conceptual problems that I don't understand yet about this that sound sort of related to what you're saying. Okay, you've understood this. Now you can go and do the full black hole jet. So you can pull up the Blanford-Zanaik paper and go through their calculations, and you can repeat all their calculations in this case with the black hole moving through the magnetic field. And I won't go through the calculation. You can look in the paper. But the point is, at the end of the day, you find a nice simple formula for what you expect the jet power to be, given by this guy. So here's the velocity of the black hole. This is a factor of v over c squared. Here's phi, the amount of magnetic flux on the horizon. And if you compare this to the Blanford-Zanaik jet power, it's extremely similar. There's just a little different numerical factor out front. V over 2m plays the same role as omega h, angular velocity of the horizon. It has the same scaling with flux squared. And then, okay, so getting back to Matthew's comment, an interesting check you can do to see that this is right comes from the membrane paradigm. So I haven't used, this was a talk about membrane stuff. I haven't mentioned the membrane paradigm at all in this section. But the membrane paradigm tells you that this black hole behaves like a conducting sphere moving through a magnetic field. And so you can build one, which we didn't do. This is called the Pioneer spacecraft. This was a weather satellite in the 1960s, a giant metallic balloon. And they launched this to measure the atmosphere, and they saw that its orbit was decaying. And so people were trying to understand why is the orbit this and what was happening is this metallic sphere was going through the Earth's magnetic field. And it was interacting with the Earth's magnetic field, and the Earth's magnetic field was extracting energy from the orbit of this guy, and this guy was gradually decaying. So in the 60s, Drell, Foley, and Ruderman set out to calculate that effect. And they found that this metallic sphere moving through a magnetic field would radiate, and here's what the power would be. This is from their paper. And it has the same b squared, v squared scaling that I mentioned in the previous slide. You can check that things make sense, just the numerical factor is a little different. And so it's a nice, it's just reassuring that the problems look so similar, because after all, like what the membrane paradigm tells you is that a metallic sphere is not a bad first approximation to a black hole. Yep. So that was just a nice reassuring thing. And now I want to comment on one more problem, which I think the memory paradigm is really interesting for thinking about. This is a more theoretical application related to something called BMS symmetries. Okay, so this picture is supposed to make you think of hyperbolic space and anti-de Sitter space. Anti-de Sitter space has this amazing property that it has a dual description in terms of a conformal field theory on its boundary. You would like to do something similar for asymptotically flat spacetimes, but it hasn't been done yet. You can try to reproduce the same success that led to this, the ADS-CFT correspondence. The first hint that this ADS-CFT correspondence existed was the fact that the asymptotic symmetry group of asymptotically anti-de Sitter spacetimes is the conformal group. So you can think about asymptotically flat spacetimes, and you can try to understand their asymptotic symmetry group. And that was done in the 1960s. Some people worked out so the set of symmetries that aren't symmetries of all space, but become symmetries asymptotically near the boundary. You classify all those. It was done in the 1960s. You get a huge group. and it's just called the BMS Group after the people who discovered it. It's much more mysterious than the conformal group. It doesn't show up naturally or obviously in field theory, but if there's some description of life on the boundary of asymptotically flat space, it should be governed by the BMS group, the same way the conformal group governs asymptotically anti-de Sitter spacetimes. And this has generated a lot of excitement recently. There's been press releases because Stephen Hawking said something about it. But it's generated a lot of excitement recently. One thing that was pointed out just a year ago by Andy Strominger is that this BMS group is infinite dimensional. And so it entails an infinite number of conservation laws. And you can think of them as energy and momentum conservation, not only overall, but at every angle. Okay, and so that's really confusing, because certainly when I scatter particles, they can come out at different angles than the particles I send in. But they showed mathematically that when you scatter particles, you also excite boundary degrees of freedom. And when you include which they called soft gravitons, when you include the boundary degrees of freedom with the ordinary energy and momentum, then indeed everything works out so that energy and momentum are conserved at every angle. And they related this to some physically observable, measurable things like black hole memory effect. In their formulation, it's very abstract and mathematical. And so one thing I found useful for me personally to understand what this is that they're talking about is I observed that this has a reformulation in terms of this membrane paradigm stuff. And so let me explain how that goes. So I mentioned earlier on that you can extend the old membrane paradigm to a membrane at infinity. So you have this fluid membrane in description of future null infinity. In particular, that fluid at infinity living on null infinity obeys just an ordinary fluid energy equation. So if sigma is the energy density of that fluid, which it turns out is related to the expansion scalar of the null generators of null infinity, the way that energy density evolves is given by an ordinary fluid equation. It has a pressure term, which is related to the surface gravity of this sphere at infinity. It has viscosity, a shear viscosity, and that term is just putting in ordinary kinds of energy. Okay, so this is all very transparent and drops right out of the Einstein equations, and it's just like the old black hole membrane paradigm except at infinity. You can think of this as energy conservation at every angle. The way to think of it that way is to multiply the whole thing by a delta function that localizes it to a single point, and then integrate over the entire sphere, and then this equation will give you an infinite number of conservation laws, one for every point in that membrane fluid at infinity. And energy is conserved at every angle in the sense that if I throw in some non-gravitational energy, or even some gravitational waves which generate shear, the gravitational waves and the ordinary energy can enter and go at different angles, but the membrane's energy density will always adjust according to this equation in just the right way, so that energy is conserved at every point in the fluid. And you can check that indeed, if you rewrite this using the formalism of Strominger and company, this sigma exactly encodes what he calls soft gravitons. So his self-gravity. You can do the same thing with the Navier-Stokes equation. So the membrane at infinity also obeys a Navier-Stokes equation, which you can show is equivalent to momentum conservation at every angle. So I found this helped demystify all these weird infinite number of BMS conservation laws that are generating a lot of excitement right now. Also interesting is that this is at the level of conservation laws. Another thing I mentioned in this paper is that there's also a connection between the two ways of looking at it at the level of symmetries. So Hong on Wednesday talked about how you can think about fluid dynamics in terms of an effective field theory having to do with diffeomorphisms, and he wrote down some symmetries that his theory comes from. It had to do, so he has a couple sets of symmetries. He allows time reparameterizations in the time direction. He allows spatial diffeomorphisms on spatial slices, and then from those symmetries gets fluid dynamics. And people here, it's a generalization of things like Sergey has done here. one of the things I point out with the paper is that over time, people have been generalizing the BMS group and slightly changing its definition. And there's very recent versions of the BMS group which exactly correspond to these fluid symmetries. So the time reparameterizations in the BMS literature are called supertranslations, and the spatial diffs in this literature are called super rotations. But there's a matching between the symmetries on both sides as well, which is neat, because you'd expect like null infinity to be governed by the BMS group. You know it's governed by fluid dynamics, so it's sort of I think a picture's coming together, although there's still a lot of details to be filled in. But already there's some interesting applications of this connection. So one thing I point out is that, the BMS group originally was only defined at null infinity, but membrane fluid dynamics works at any horizon. And so you can use that fact to generalize the BMS symmetries and stuff to like event horizons and other horizons. When you start with the membrane fluid evolving and then reformulate it in this symmetry language. Yep. And then since my time is up, I'm going to skip the last couple slides because just to end on time. But all of this has an analog for electrodynamics. So there's an asymptotic symmetry group for electrodynamics of large gauge transformations. There's charge conservation at every angle. It shows up in the membrane paradigm because the membrane satisfies this charge continuity equation. You can term by term match with this other way of thinking about the story. And there's also a connection at the level of symmetries. Yep, also a connection at the level of symmetries. Yes, and then that's just an example. So to summarize, I kind of talked about four things. One is the membrane paradigm and how you can extend it to describe a membrane at infinity, and that turns out to be useful. I touched on jets from spinning black holes and how the membrane paradigm is useful for understanding the universality of this omega F. I talked about developing the theory of boosted black hole jets. And finally, I talked about some recent work using the membrane paradigm to understand the BMS group. And for the future, there's a lot of things to do. Now that we understand these boosted black holes analytically, the next natural step is to just simulate it and see what happens. So you can repeat the same simulations I showed pictures of, but using moving black holes, and you can watch what happens and do all the same things. Try to understand that problem with the same level of detail that we understand spinning black holes. There's more analytical work to do with that problem, so it'd be fun to find semi-analytical solutions for the magnetospheres of moving black holes. It's a harder problem than spinning black holes. There's less symmetries, but you can simplify the problem by going to different limits, like making the velocity really large or really small. You can also simplify that if you just want any analytical solution, because we have none right now. You could simplify the problem a lot by going to higher dimensions where there's black branes which have translation invariance, and then that would make it easier to solve. There's a part of my interest in this is not only LIGO, but also there's some really interesting conceptual questions, which is that there's another way to extract energy from black holes, something called superradiant scattering, where you scatter waves off. It's sort of, from thinking about spinning black holes, we thought it was equivalent in some sense to jets. But the weird thing is that for boosted black holes, there's evidence that you can extract energy using jets, but there's also evidence that you can't extract energy using superradiant scattering, which is really weird, and it would be good to understand why one seems to work and not the other when they seem so closely related. So that's going to be a fun conceptual problem. And then finally, there's a lot to do mapping out this sort of dictionary between the BMS group and the fluid interpretation of it. And then you can extend it to all different horizons. So it'd be interesting to do the same sort of thing in de Sitter space on the cosmic horizon. All of these, the cosmic horizon of de Sitter space also has a membrane description. So it'll also have these BMS symmetries, and it'll be interesting to work all of that out. Yep, so that's the whole talk.
So to take since you talked about ADS, if you take a black hole in ADS space and apply membrane paradigm, now you would say there should be another membrane at infinity. Well, in that case, infinity is the boundary, I suppose. So have you thought about that? What that would be the context of?
Yeah, it's so infinity, right? And so there, infinity is time-like, and so you don't have that. So you have to choose your boundary conditions. So here you're sort of forced into the boundary condition that only all waves are outgoing. ADS, you have more choice over what boundary conditions you want to use, and so the conditions of the membrane will depend a little on those choice of boundary conditions. But it's definitely been thought about. So earlier when I was mentioning different ways of deriving membrane paradigm, the last bullet point was work by Hong Liu and company, where they think of it in ADS. He goes to ADS, and then he points out, so in ADS, the radial direction acts like the scale in a renormalization group flow, so that the UV is at large R, and the IR is at the horizon, and so different radii are different scales. And his way of, and then he derives the membrane paradigm at the horizon as the IR limit of the CFT on the boundary. So as that CFT flows to large,
but you have new ingredient now, which you introduced, right?
So it would be so I'm not sure if for some choice of boundary condition, if you use, so when people do ADS-CFT, they have to fix some boundary conditions. For the same boundary condition, the membrane at that boundary should look like the CFT. And I think that's talked a little bit about in Hong's paper, actually, because he has to define the membrane in some sense on a cutoff surface at every radius, and then look at how it changes with scale. So implicitly, it's sort of in his paper somewhere, yeah.
So this problem of orbital motion powering jet or powering energy emission, can you just treat the black hole as like you said, a metallic ball with resistivity 77 ohms, and you know the strength of the magnetic field, you know the orbital velocity and so on, can't you just on the back of the envelope calculate how much power can be emitted from this?
I would say that you can now, and that's what I showed that it had been done in the 60s by Drelfel and Rutherman. But I personally, 2 years ago, would have wanted to go through the GR calculation slowly, which is what I do in the paper, to convince myself that it really works that way. But now I'm convinced that in the future, don't go through the whole GR calculation. If you just need the estimate, just do it that way. But I think someone had to go through slowly and check that it would work. But yeah, I agree. That does work out that way, actually.
Yeah, I didn't mean to.
Yeah. So in the future, I think it would be fun to just solve some Newtonian no gravity, just electrodynamics problems of conducting spheres moving through different field geometries. No one's thought about that problem that much, but now there's a lot of motivation to just think about that problem a lot. Yeah, but compute the power radiated
but
as...
You mentioned that they correct scaling, but not the coefficient. Why is that? Presumably, if one doesn't cross
No, it won't. I mean, the coefficient, it's off by some small order unity thing. It's not a major difference. Mm-hmm. But because of the curved geometry of the black hole, it's never going to be exactly the same. Mm-hmm. I mean, so so there's three things. There's the black hole problem done the traditional way, where there's an event horizon and an interior, and nothing special at the horizon. There's the black hole problem done in the membrane paradigm with no interior and a membrane at the horizon cutting off space-time. That has to give you, those two calculations have to give you the exact same answer with all numerical factors. Then there's a third thing, which is like a Jackson E&M problem of a conductor moving through a magnetic field in Minkowski space, which is a different problem, and it's going to not have the exact same numerical factor, but because of the analogy, it's at least going to give you the right scalings. Yeah.
Does that estimate indicate that there are electromagnetic countercurrents to LIGO events? Isn't that sort of the most important question?
Yeah, so when you actually compute the power in the last phases of in-spiral with a strong neutron star magnetic field, it's significant, and it's probably observable. But there's...
Does LIGO have enough directional information?
Well, I mean... so that requires more work to make those estimates. Yeah, more work needed.
The flip side is the gravitational waves signature. Mm-hmm. Can you compute what the deviations from the neutron star black hole predicted waveforms would be as a function of magnetic field?
That's what I was sort of mentioning with earlier. Yeah, some back of the envelope calculations suggest that these jets, they only become significant when things are moving relativistically because of the v/c² factor. And in those phases of the merger, the gravitational waves are taking away so much energy that this is a really small perturbation that's not really affecting the orbit of the gravitational waves very much.
But they need a template to search the data, so even if it's a small deviation.
Even if it's really small, maybe, yeah. My instinct is not important, but maybe if it had some crazy, really good sensitivity. Yeah, I don't think it's...
I think the Jackson problem and the weather balloon problem are probably done for a sphere moving through an insulating medium.
Mm-hmm.
I was wondering if you were considering the magnetosphere to be insulating, or was it a conducting plasma?
Yeah, there's some assumptions in the derivation that it's a force-free plasma.
You have a force-free.
Yeah, so that'll be a little different from what Jackson would
so that
do.
might be another reason for difference. Maybe order unity differences.
Yeah, generally the luminosity of these electromagnetic things is set by to order of magnitude, or what is, I can't think of the name of it. It's escaping me, never mind. Okay. Other questions?